Welcome to another lecture video. We're going to be looking at what we call L2 theory of Fourier series today. I wanted to catch you up on what you can expect this week. This is a shortened week from normal, but we will finish up all of the second unit today, or this week. Starting today, we're going to be looking at the L2 theory of Fourier series. I already have the lecture notes up for that. I'm a little late in recording this video today, so it'll go up late on Monday. My apologies for that. And then we'll have another video on Wednesday talking about differentiating and integrating Fourier series and some of the things you have to be aware of when you do that. There will be some additional readings for that I'll post on Wednesday. Actually, I'll probably post those on Tuesday, but I just want you to be aware of that. And then Friday of this week is Good Friday, so we don't actually have a video lecture planned for that day, but you should start working on Quiz 7. The practice quiz for that is already up, and Homework 7 is already up as well. You can already be working on that. In fact, most of that homework set can be done. I know it's due on Easter. I really don't want y'all to be working on this over Easter. So make sure that you get in and get that taken care of. So let's talk about L2 theory today. We've talked a little bit about what the L2 space is. We're going to say a little bit more about it today. But we're going to start with a reminder here. This is the full Fourier series of a function. So suppose you have a function defined on the interval from minus L to L, then that function can be represented by the full Fourier series, and here are the coefficients for that full Fourier series. As a reminder, a couple of terminology pieces here that we haven't used yet, but I want to make sure we understand. The first is that when you look at the full Fourier series, each of these terms of the series are called the harmonics of the Fourier series. So this is the nth harmonic, and I really should be a little bit more rigorous here about talking about this. This formula is really only for n equal to 1, 2, and so on. If you look at the full Fourier series, the zero term is a naught over 2. And so the zeroth harmonic would actually be a0 over 2. The first harmonic would be a1 cosine pi x over L plus b1 sine pi x over L. And all these they are the waves, they're called the harmonics. They're the waves that build the signal or the function f of x. These are sort of the signals that compose the function f of x. Another way, and we're starting to get into some signal processing terms here, which is where this course would go next. So if you have a chance to take a signal processing course or something like that through the physics or engineering department or in graduate school, this is kind of leading into some of the topics there. The frequency spectrum of a Fourier series is defined to be this set of values. And just to make sure we understand what this set of values is, it's really just, these are waves. And so if you take the square root of an squared plus b squared, it's the amplitude of that wave. So the frequency spectrum here, this is the amplitude of the nth harmonic. And if you take a naught over 2 and you square it, or take the square it, then take the square root of it, right? Which is what you're doing here. So the zeroth harmonic would be, so the zeroth frequency would be the square root of a naught squared plus b naught squared, but b naught squared is 0 because there is no b naught harmonic. And so you have the square root of, it would be a naught over 2. Well, we're almost there. It would be a naught squared over 2, which is where this term is coming from. So this is defined as the zeroth frequency, and then these are the nth frequencies, which are really the amplitudes associated with the nth harmonics. But it's part of what's called the frequency spectrum. And then you have what's called the energy spectrum, which is simply just these values squared. For instance, gamma naught squared would be a naught squared over 2. And then gamma n squared would be an squared plus bn squared. We're definitely going to remember that one for later. And I have a Maple file where I've gone in and actually calculated these spectrums just to kind of give you an idea of what it is we're looking at here. So if you look at the Fourier series examples, Maple file 13, I have an example here of a piecewise function. And with that piecewise function, we're looking at, the odd extension, the even extension, plotting all those different extensions, just like we've done. And here are the Fourier series, and I want in particular to pay attention to this full Fourier series here. So if you take this full Fourier series, calculated it the way that you would be used to, down here right underneath it, so if we go a little bit further, I've defined the frequency to be the square root of those coefficients squared, just like we would normally do. I've also attached to it the point 0, 0, because just to have a start for this frequency spectrum. So this is the frequency spectrum, and all this graph is it's a plot of the harmonics are along the bottom. So this is the 50th harmonic out here, which are the higher frequency terms. And these are the lower frequency terms here. And then remember, the y-axis of this graph would be the amplitude. So the larger the amplitude, the more that harmonic contributes to the overall signal. So if you're looking at this particular function and its Fourier series, this frequency spectrum here tells you which frequencies contribute to building that function. And the lower frequencies typically will have the higher amplitudes. It's very rare to see functions with higher frequency spectrum, large amplitude values, because generally the higher the frequency, the less involved those frequencies are, which is why the error is low if we chop them off. The less they are involved in recreating the functions that we're representing. This kind of stuff is really the stepping stone for looking at things like mass spectrometers. Mass spectrometers actually shine light through compounds, and they record the wavelengths of those light, and then they play it back across what's called the mass spec, and it basically creates a graph that looks just like this. It shows you which waves were excited, which wavelengths were excited the most by the light shining through it, which tells you the presence of certain components in that compound. It's really just an application of this stuff that we've been dealing with. But that's, for a chemistry course, different course altogether. Just understand that this frequency spectrum is a really important thing in a different course. We're not going to deal with as much of it today, although we will talk about it here in a little bit. All right, so those are just some terms that I kind of expect you to know. What is the harmonic of a Fourier series? What is the frequency spectrum? What is the energy spectrum? I don't think you really have any homework questions over these, but they are just some terminology that's not really in your text, and I wanted you to be aware of it. All right, so this is a big one. It's something called Parseval's, technically inequality here, but we're going to talk about Parseval's equation. What I would like to do, starting with, is show you that for a Fourier series representation of a function, that we have this property. And this may not seem like a big deal, but it's actually a huge deal, because what this says is for the full Fourier series, you have this sort of relationship. In other words, the sum of this is the energy spectrum. The sum of the energy spectrum is related to the norm squared of the function. So the norm squared of the function is related to the energy of the signal. So if you're adding up the energy spectrum, that gives you, in some sense, the total energy of the signal. We're going to talk about that here in a little bit, but I actually want to prove, so this is Parseval's equation. And the assumption here is that you have a function that's represented by what we call a generalized Fourier series, or an orthogonal expansion. So if you have a function that's written in terms of an orthogonal expansion, then the sum of the energy spectrum of that expansion is equal to the norm squared of the function only in the case where you have the full Fourier series. Otherwise, the energy spectrum is less than the norm of the function. But if the coefficients here turn out to be Fourier series coefficients, you actually get equality. And it's actually a big deal that the full Fourier series makes this inequality an equal sign. And I'm going to show you, I'm actually going to prove to you that this result is true. So we're actually going to prove this. This is not in your textbook, but I think this is a good exercise for us to look at to understand a little bit more about what's going on here. And the norms, all of the norms that we're looking at here are the standard L2 norms. We'll talk about a bit more about L2 spaces in just a second. So let's start with just a reminder of what's going on here. If I look at the norm squared of a function, and remember the Fourier series is defined on the interval from minus, the full Fourier series is defined on the interval from minus L to L. And so if we say that f is an L2 function on the interval from minus 1 to 1, then that means its norm is given to us by, normally it would be the square root of the integral, but since we're squaring it, there's no square root. So the norm here would be minus L to L of the function f of x squared dx. And really, we don't need the absolute values here, because it's just the function squared. Remember, the norm here is the same thing as the inner product of f with itself. And yeah, because the square root of the inner product of f with itself is the norm. So the square takes care of the square root. So this is just your standard inner product like we've talked about before. But that's equal to the norm squared of the function, which is related somehow to the total energy of the signal carried by the function f of x. So we know that this is what's kind of going on the right hand side here. In fact, 1 over L times that. So let's just write that in. But first I want us to consider also that what I'm talking about here is the function f of x has a Fourier series representation. So I can think of f of x squared as f of x times f of x, but what if I take this f of x here and replace it with the Fourier series? So that would be the sum, well actually, a naught over 2 plus the sum, n goes from 1 to infinity, of an cosine n pi x over L plus bn sine n pi x over L. And so what we're going to do here is we're going to take this and we're going to replace the f of x squared inside this integral with this term. So, and I'm going to divide through by L to make the calculation go a little bit better, and also to mimic the fact that we have a 1 over L here. So 1 over L times the integral of this would be, well actually let's just do it without the integral first, and I'll put the integral in here in just a second. So we have f of x squared is equal to what we just wrote down over here, and that is f of x times a naught over 2 plus the sum, n goes from 1 to infinity, of an cosine n pi x over L plus bn sine n pi x over L. Okay, if we integrate both sides from minus L to L, and then divide both sides by L, what you see is that on the left-hand side here, this is the same thing right here. This is the same thing as the norm squared divided by L, or the norm squared divided by L. So this part right here is the norm of f squared divided by L, which is the right-hand side of this equality that I'm trying to prove, this Parseval's equality. Okay, so let's think about what's going on the right-hand side here. I've got f of x can be distributed. In fact, the integral and f of x can be distributed across this sum. So if I distribute it across the sum, what it would end up looking like is a naught over 2L integral minus L to L f of x dx. That's the first piece here. So distribute this to this and pull out the a naught over 2. And then if I distribute it to the other pieces, I can bring the integral inside the sum because I'm assuming that the function is an L2 function. I'm assuming certain convergence properties, piecewise continuous. As long as the function f of x is piecewise continuous, I'm allowed to do this. So if I bring this in, we would have something like the following. So this would be an integral minus L to L of f of x cosine n pi x over L dx. Because I can bring the integral term in up until I meet an x. So there's where I meet the x. The an's a coefficient. I can pull it out. I also have an x term here. So this is going to be plus bn integral minus L to L f of x sine n pi x over L dx. All right, so that looks good. Now, if we take a look at what's over here on the left, this term right here, you see something very interesting happening. The 1 over L integral minus L to L of f of x, that's just a naught. So if you look at the way these are defined, go back here to our Fourier series, a0 would just be 1 over L integral minus L to L of f of x dx. So that means if we look at this, this is really a naught times a naught over 2 plus the sum. N goes from 1 to infinity, a n, and then what is this? This is just another a n, right? If you go and look, this is the formula for the coefficient a n. So we have 2 a n, so that's a n squared. This is the coefficient for bn, so that's bn squared. And voila, we've got exactly what it was that we needed to prove. And that is the sum of the energy spectrum is equal to the norm squared of the function divided by L if we're looking at the full Fourier series on the interval from minus L to L. In general, for an orthogonal expansion, the sum of the energy spectrum is less than the norm squared of the function. But in the case of the Fourier series, either Fourier sine, Fourier cosine, or full Fourier series, it turns out that the sum of the coefficients is actually equal to the norm squared of the function, which is a really big deal. And we're going to track that here with a couple more examples. So once again, how do we interpret this result, right? So the sum of the energy spectrum of a signal is the signal's total energy. So think of it this way. The norm squared is given to us by this. This is the average value of this function squared on the interval from 0 to L. This is called the total signal energy of f. And what we just proved is the total signal energy of f divided by L is equal to the sum of the energy spectrum for the full Fourier series. It's pretty cool. There's a lot that you do with this in a signal processing class. I taught a special topics signal processing class back in 2015, and we used this result a ton in that class. I don't know if there's really a course on campus right now that would make really good use of this result, but if you go on to do signal processing or electrical engineering or something like that, your graduate school courses, it's all about this kind of stuff. All right, let me remind you of some definitions here. Well, actually, this is a new definition. What is the L2 space? The L2 space on the interval from a to b is the set of all functions defined on the interval that are real valued, whose integrals, the square of their integrals is less than infinity. This means square integrable. So this is the condition. So the L2 space is the set of all square integrable functions on the interval from a to b. We're primarily used to, and in most of our examples, we've been looking at L2 minus L to L. A lot of our Fourier series examples have been. Or we've been looking at L2 0 to L. So most of our examples so far have been functions that have been square integrable on one of these two intervals. It has our standard inner product. So this is just called the L2 inner product. And the norm is just our standard what we call L2 norm. Sometimes you'll see a subscript 2 there, but typically when we're talking about norm, it's this norm. The L1 norm would be not the square. It wouldn't be a 2 here, but it would be just a 1. So you'd be integrating the absolute value of the function over the interval. These last two notes here are more for people that have maybe taken an analysis course. The first says that the space of L2 functions is the completion of the space of the continuous functions. So in other words, if you have a sequence of functions and all of these functions live, say, in the space of continuous functions, and you look at the sequence, that the limit of that sequence, we'll call that limit f, that function must be a member, well, is a member of the L2 space on the interval from a to b. So the completion of any sequence of continuous functions is an L2 function. That turns out to be a big deal in an analysis course when you're looking at the completeness of the Fourier series and things like that. The completeness of the Fourier series representation. We don't deal with that in this course, but I just wanted y'all to be aware of that. If you've taken an analysis course, you may have heard of a complete space. And so if you have, great. If you haven't, then probably not a big deal. It's certainly not something you need to know necessarily for this course. All right, this is a very important theorem. I think your textbook calls it the best approximation theorem. It says, suppose you have a function that has an orthogonal expansion. Now, these don't have to be Fourier series, but if they are Fourier series, if xn is the sine n pi x over L orthogonal set that we define the Fourier series on, then the coefficients Cn minimize the error. So the best expansion that you can do is the Fourier coefficient, right? Those are the best. So this is how we define our Fourier coefficients. It's what we call, the generalized Fourier coefficients. And what this theorem says is generalized Fourier coefficients give the best error approximations, meaning they are the fastest to converge. They give the best pointwise error across the interval. We're studying the best possible approximations when we study the Fourier series. They're better than Taylor series, way better than Taylor series. Now, do they converge faster? In some cases, yes. In some cases, no. But they are the best in terms of ultimately getting a good approximation of the function. They will give you the best error. That is such an important result that I want to prove it. And the proof is interesting. You can learn a lot from the proof. Just how to manipulate inner products and things like that, which is why we're going over this. I want you to at least been exposed to this stuff. So here's the proof. Suppose that we have a function that is in L2 on interval from a to b, and it has an orthogonal expansion given by this series. So we have a f of x is approximately given to us by this. This is where xn forms a complete orthogonal set. So where xn is a complete orthogonal family on the L2 space. So you're representing an L2 function. You're using a complete orthogonal family of L2 functions to do it. That's the setup that we have. Okay, so we're going to define the total error of the approximation by En, where En squared is equal to the norm squared of the difference between the function and its approximation. So this would be the approximation and the function, and this is the norm squared of the difference. If it's just the norm of the difference, that's the size of the difference between these two, that would be the error. The way that this is defined is it's the integral from a to b of the sum, n goes from 1 to n of Cn xn minus f of x squared dx. So that's the definition that we have here. And you could think of this as, this is the pointwise error in a sense, because it's the square of the pointwise error, but then you're integrating it across the entire interval. So it's the square of the total error, right? You're basically taking the error at each point in the interval, adding it up continuously. It's the error squared, so we don't have to worry about positive or negative error, right? So it's the total magnitude of the error, but it's squared. And so this is the total error squared in some sense. So this, if you look, I can FOIL this out. This is a term squared. Let's FOIL it. It's kind of interesting to have to FOIL a sum if you haven't done that very often. But it would be, this term squared, minus, then it would be 2Cn xn f of x, right? You're taking twice this with this, right? Because it'd be this times this minus this times this. There'd be two of them. All of this is inside the sum. Okay? Then, outside the sum, you would have f of x squared. Okay, so this part's in the sum, this part's out of the sum. So when you're squaring this, you just have f of x squared dx. All right, so let's keep going with this. I want to interchange integral, and basically I want to distribute my integral across this. If I do that, then you'll get something that looks like this. Once again, because our function is an L2 function, we have certain conditions that are met that let us interchange integration with summation. So everything here is valid. And here's where things get sort of interesting. Remember, the inner product is simply, the inner product of two things is the integral from a to b of f of x times g of x. But here we've got these two things squared. So this is really just defined as the inner product of Cn xn with itself, because there's two of them. Then this is 2, take the 2 outside the integral. This is this function times this function, so it's the inner product of Cn xn with f of x, plus then this is the inner product of f of x with itself. So I can write everything that's here in terms of inner products. Okay, well, we know if you take the inner product of something with itself, That's the same thing as the norm squared of that thing. But notice the cn squareds, those were just coefficients. I could have pulled those out. So I can factor a cn out of this thing, in which case I'm left with the norm, I'm left with xn inner product with the xn, which is really just the norm of xn squared. This is minus 2. Pull one cn out of this. Cn squared. Pull one cn out of this, and then this would be xn with f of x inner product. There's no norm there. But this last one is the norm. This is the norm squared of the function f. Okay, if we keep going, I'm going to pull, or I'm going to divide the norm squared of the xn term. I'm going to pull it out of these two terms. These are inside the sum, so I'm going to factor this term out inside the sum. All right, what we end up with here, and actually let me just put the cn in there. So we've got the cn squared in there, minus 2 cn. This one's going to be a little bit tricky. So there I've factored out the norm squared of x from these two terms. Okay, I want to complete the square on this. So you remember how to complete the square. You've got cn squared minus something cn. So what you do is you take the middle term, you divide it by 2. So get rid of the 2 here. So I'm looking at what's multiplied by cn here. So you take the coefficient of the cn, divide it by 2, getting rid of the 2, and you square it. So I'd square the top, and I would square the bottom. Okay. And then I would add and subtract that in. Okay, so here's the way it would go. All right, so we're going to add it in. So it's this term squared divided by the bottom squared, which would be now to the 4th. Okay, so we've added that term in. So what we got to do now is take it out. So outside here, I've got this, but then I also have to subtract this term out, but with it comes the sum, right? You can't forget about the sum. So this is going to be, give myself enough room here. This is going to be minus the sum. N goes from 1 to n of, it's xn squared times this term. So we would have that. So, all I did was took what was inside here, I completed the square on it, so I added this term in, I also subtracted that term out. So I haven't changed anything. The reason it's squared here instead of the 4th is I multiplied through by this. So if you multiply this in, it's really just xn squared when you take it out of the sum. Now, if things went according to plan, and we did indeed complete the square, then this is a perfect square inside this. And how does it factor? Well, it factors perfectly into this. So it's this term that we left out. That's what it factors perfectly into. Check the math if you like. So it's all of this squared. Yeah. So here's the thing. And we still got all of this other part left over. So here's the thing. This is the total error. That's what we're looking at here. String of inequalities. We're finding the error squared. When is the error minimized here? What value of the coefficient Cn? Cn only appears right here. What value of Cn will minimize this? Well, if Cn happened to be the same as this, then all of this would go away. And sorry, there shouldn't be a square there because you're going to square it. You're going to square it here. So it's this. So if Cn is equal to this, then the term is minimized. We know that because all of these are positive terms. There's no Cn here. It doesn't affect it. That's a positive term. To get the error as small as possible, I want all of this term to go away. Cn can affect it, so to get this term to go away, Cn has to equal this. So if Cn is equal to this, then the term is minimized. But what is this? This is the formula for the Fourier series coefficients. So the Fourier series coefficients minimize the total error of the approximation. They are the best approximating set of functions, best approximations out there for functions on the L2 space. Okay, so where do we go from here? Well, it turns out that if you have an orthogonal expansion, that you always have this property that the sum of the square of the coefficients and the norm of the eigenfunctions squared is less than or equal to the total energy of the signal, and that will always be, since these are L2 functions and this function f is square integrable, this will always be less than infinity. Now, it turns out that if you have a complete orthogonal family of functions like the Fourier series are, then this is actually equal to each other. So this is something called Bessel's inequality. And in the case of a complete orthogonal family, if the xn's, just like with the Fourier series, that should be a lowercase n. If the xn's are a complete orthogonal family, then it's actually equal. You actually get equality between these two. This is also called Parseval's equality or Parseval's identity. So I want to prove that this thing actually holds. Well, it's actually pretty easy to prove that because we just did all of the heavy lifting here on the previous proof. So notice what the previous proof said, that if we use the Fourier coefficients, then the error is minimized. This term goes away. We're left with just this. So by the previous proof, by the previous result, the error squared, which is a positive value, no doubt, is equal to, let's see here, what did we have left over from last time? We had this thing squared minus the sum. N goes from 1 to n. Squared over squared. This is where the function f of x has this approximation. So the error squared ended up with just this. If we assume where this is this and where Cn is that. So if we're using the generalized Fourier series, then we obtained a minimal error, and on the last line of that proof, this is that minimal error. Well, minimal error squared in this case. So look at what this says. This if you look at this term right here, what is this? And we'll look at what the CNs are, and then look at this. isn't it just Cn squared times the norm Xn squared? Right? And the reason you have to multiply through by the xn is because if you square this, you'll get an xn to the fourth, and you've got to cancel that to leave an xn squared on bottom. So this is just Cn squared, Xn squared. We know that's greater than or equal to 0. So this is where Bessel's identity comes from, is that the norm squared is greater than or equal to that sum, because they're greater than or equal to 0 on that line. Right? So that's where Bessel's inequality is coming from. But let's take it even further than that. If f of x is an L2 function, then we know that the norm of f is less than infinity. So we can actually say this. And when the set Xn is a complete orthogonal family, as is the case with the Fourier series, then it actually turns out, and I'm not going to prove this one, but it actually turns out that this is an equality. And one more added thing, if the norm of my orthogonal basis is 1, so if all the functions have norm 1, given any orthogonal family of functions, you can do something called the Gram-Schmidt process given any set of functions, you can use Gram-Schmidt to orthogonalize them, so you can come up with these orthogonal families very easily. And then you just divide every member of the family by its norm, which would give everything in the set norm 1. If everything in the set has norm 1, the term we give to that is orthonormal. So if you have an orthonormal complete orthogonal family, then notice what this says. This says that if you add up, so you add up all the Fourier coefficients, that sum does not diverge. This is something called square summability. So if you have a function that is square integrable, meaning it's a member of the L2 space, then the Fourier coefficients of that function's representation are square summable. And that turns out to be an amazing result. That result is used in many, many different places. It's used to find infinite series, all sorts of things. All of these results can be summarized with this theorem. And this is a big theorem in representation theory. It's called the Riesz-Fischer theorem. And there are abstractions of this theorem as you go into graduate school. But basically it says that all of the following things, if you have a complete orthogonal family, so complete orthogonal family, I'll talk about that definition more here in just a second. But if you have a complete orthogonal family representing a function on the L2 space, these are the generalized Fourier coefficients. So if you're living in the world that we're living in this class, then the following things are all equivalent. A function, it belongs to the L2 space, then that function's Fourier series will converge in the L2 sense. We don't have to worry about convergence. If we use this representation, then we're good. And we'll be able to actually sum, we'll be able to find the total energy of the signal by summing the coefficients times the norm of the xn squared. which is Parseval's equality that we talked about in just the previous proof there. So Parseval's equality holds. You get this nice convergence property as long as your function's on the L2 interval. So a couple of notes here. The first note that I'll start with here is when we talk about a complete orthogonal family, like this theorem does, complete orthogonal family, another name for that is an orthogonal basis. So if you have a complete orthogonal family, then what we've talked about today is enough to give you that all of the functions xn are linearly independent and that they span the space, meaning any function in the space can be represented in terms of them. And they are the best approximating ones. In fact, they exactly approximate. They give the least error in their approximations. All of those things scream basis. So these actually form an orthogonal basis, and we used them as such when we use separation of variables. We used the fact that the family of sine, the family of cosine, n pi x over L is an orthogonal basis to create a basis for the solution space. That's the premise upon which separation of variables as a technique is built. And it's nice to see that the proof bears it out, that we do indeed have an orthogonal basis in this case. One other thing for you to kind of hold on to here is suppose that my orthogonal basis is the set of functions sine nx and goes from 1 to infinity. So this would be like it'd be n pi x over pi, right? So this would be orthogonal set of functions on the interval from minus pi to pi. So if you're doing a full Fourier series, Fourier sine series representation on minus pi to pi, this would be your orthogonal family. So that is a complete orthogonal family. Which means there exists no other function f of x in L2, what would be minus pi to pi, such that the inner product of sine nx f of x is equal to 0 for every n. What this is, I'm talking about the definition of what it means to be a complete orthogonal family. You know you have a complete orthogonal family if there's no other function in the space that you can add to the family such that the inner product of that function with every other member of the family is 0. There's nothing that's pairwise orthogonal to everything else in the set. You've lumped in everything else in the space that's orthogonal to everything else in your space. Right? So the only function that it would be orthogonal to everything would be 0, right? So what I should say means there exists no other function f of x in L2 minus infinity to infinity that's non-zero, such that this is true. Because the 0 function is always orthogonal to everything in the space, but here you have every non-zero function that's orthogonal to every other member of this family. What's really important here is this is an infinite basis, and I know a lot of you that are used to working with bases aren't used to working with infinite bases. And so if you have an infinite basis set, you can't remove a member of that basis set. So note that removing even a single member of this infinite basis will make it cease to be complete. For example, if I looked at the basis consisting of sine, but I started it at 2, this is an orthogonal family, but it's not complete, since if you looked at sine of x with sine of nx, this would be equal to 0 for n equal to up to infinity. So this is a non-zero function that still lives in the space that's mutually orthogonal to every other member of that set. So that set would not be complete. Removing there's an infinite number of them, and there needs to be an infinite number of them, because the removal of even one of them would cause it not to be complete, which would cause us not to have these nice relationships that the Riesz-Fisher theorem talks about. So Parseval's equality, this is actually really useful for finding infinite series, for finding infinite sums. And I'm not going to do an example of that, and I don't think I put one on the homework this year. I have in the past. But it's really useful for finding infinite sums. I would like you to check out example 3.5.2 in the text, along with problem number 11 in section 3.5. If you have a little bit of time, just take a look at those, and you'll see how really useful this equality is for proving those things. All right, I know this was a very heavy on the theory lecture today, but there are some really, really interesting nuggets of information to come out of this. Things that'll set you up well if you go into grad school. You'll at least heard of some of these things. We need classes like this every now and then. Give us a break from all the applied stuff and look at some of the pure mathematics behind what's going on here. All right, we'll look at whether or not you can differentiate or integrate Fourier series coming up on Wednesday. And then that'll be our last topic for Unit 2. And we'll start talking about the test. I think it's coming up next Wednesday. We'll start talking about the test over this weekend. All right, y'all have a good day, and I will see you later.